we are missing a quite important type of terms. All the ones which had with the interaction with the electronic spin, they were missing. And the reason they were missing is that in the normal Schrödinger equation there is no spin of the electrons, because Schrödinger equation is basically spin-free. Although, I mean, if you look at what you've seen in Hart-Fock, and also when we talked about electron correlation, the wave function we use, they have the electron spin in there, because we write them as Slater determinants made from spin orbitals. So one sort of has built that in there due to the Pauli principle. I mean, Pauli's principle required that you sort of treat the spin and you have it in there. But there's no direct interaction due to the spins in the Schrödinger equation. But you have that in the Dirac equation. And in the Dirac equation, it's not just, I mean, it's not added to it in a way that, I mean, you can do that with the Schrödinger equation. That's what we're going to do now. We look at how does the spin term, or term depending on the spin of the electrons, looks like. And in a way you can look at it and compare with the experiment, see what kind of interaction that is. And then we just add it to the Schrödinger equation. That's not the same in the Dirac equation. In the Dirac equation, it's actually really more the way that it just pops up. Analyzing the terms in the Dirac equation, you realize that spin is included there, which in a way is mysterious in a way, or strange, or whatever you want to call it. So the way one can, quotes, derive the spin terms is to start from the Dirac equation and then take a non-relativistic limit of the Dirac equation, and but keep sort of the terms which come from the spin. And all the ones who are interested in see that, you can see that in my course in block 3, where we do that. Sort of derive the Dirac equation in quotes, or get to the Dirac equation, and the first thing we do with it is then destroy it again and pull it apart and get the individual contributions. And one of the things you also get then is, of course, spin-orbit coupling, because the spin-orbit coupling is in the Dirac equation built in, but obviously it's also missing from the Schrödinger equation, and you have to add it extra to it if you want to. But what you get then, you get sort of, I think it was this way, yes? So we get spin-dependent terms or contributions. And spin is the electronic spin, because the nuclear spin we had already added to it as the external perturbation. But this is not an external perturbation. This is sort of really part of the Hammond operator. And we're not interested in spin-orbit coupling, but we just want to have interactions of the electronic spin with the external perturbations, external or internal perturbations. So from the Dirac equation, we get what one calls the Zeeman, or could call it the Zeeman term. In general, if you talk about a Zeeman term, then this is a term, the interaction with an external magnetic field and some kind of angular momentum or momentum in general. And that term then looks sum over all electrons. Now we have the electronic G factor, the elementary charge, 2 times the mass of the electron. And now we have the spin operator of the electron, which is a vector, like the angular momentum operator. And then times the curl of whatever vector potential you have at the position of that electron. Like this. So that is what you can derive from the York equation. You actually can sort of then have a discussion about whether spin is a relativistic effect or not. And I've heard both opinions. People saying clearly no, this is not a relativistic effect. This is just a property of all elementary particles that they have spin. And has nothing to do with special relativity. So it's not a question of the speed of a particle getting close to the speed of light. And then things happening, meaning normal classical Newton's mechanics not being valid anymore, and you have to go to relativistic mechanics. And it definitely has nothing to do with that. Because, I mean, there's no, the other thing is, of course, there's no classical analog to spin. I mean, it's not the electron rotating around itself. Because if it would be rotating around its own axis, it has to have an extension. Right, now that part I hope you can recognize. The curl of a vector potential. Because the curl of the vector potential, that is basically, that's the implicit definition of the vector potential. And this is just the magnetic field at that position. That is from classical electromagnetism, sort of the definition of the vector potential. And so what we actually have here is this extra term as just an interaction of E to ME as times a magnetic field at that position. And we had on Tuesday already similar expressions where we had interactions between moments and fields, always being minus the moment scalar product with the field, which then must mean that this here is actually the magnetic moment of the spin of the electrons, or to be more precise, minus the magnetic moment of the spin of the electrons. Because then we get the expression we had before, minus like this, which is the interaction between a dipole moment and a field. And I mean, that sounds very natural. We have an interaction of the magnetic moment coming from the motion of the electrons. Charged particle moving in space have an angular momentum. I mean, having an angular momentum, have a magnetic moment. And that magnetic moment, the energy of that magnetic moment depends then if you have an external field. And since the electrons have also spin moment, you will have the same effect there.